Hello world. Okay, so f prime of x, our first goal on this problem. What do we got? 3x squared minus 8x plus 1. All right, not too bad. Next, critical values. What do we do to find critical values? We set it equal to 0, and then we could use the quadratic formula or try and factor. This probably doesn't factor. All right, so we have to solve for part B, 3x squared minus 8x plus 1 equals 0. Did I get that right? And generally, I think, can I factor this? And if I don't see it quick, I forget about it. Completing the square I like to do, but only if that's a 1x squared and an even middle term. Otherwise, I whip out quadratic formula. The quadratic formula says x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c. And I usually slow down with the minus part there because that's where I'm likely to make a sign error, all over 2a. But usually I feel pretty comfortable about squaring b in my head. So what do we got? We've got, that's 64 minus 12, is that right? Which is 52 on a good day. So we get 8 plus or minus the square root of 52 over 6. And usually with these, I don't really care too much about simplifying them. But if you love that thing, we could do that. So I would need to factor 52 to see if this simplifies. 2 goes in there 26, 2 goes in there 13, I get that right? So 2 pops out, that does simplify a little bit. 8 plus or minus 2 square roots of 13 over 6. 2 can be factored out of the top, right? So we end up with 4 plus or minus square root of 13 over 3 once we factor that 2 out and reduce. And then it's time for a calculator. Anybody already calculate these?
2.53518.
Okay, so let's just 2 decimal places, so 2.53?
Yeah.
Okay. And the other?
13.
0.13. Anybody else get similar results about that? Okay. So the approximations are good just because I need to throw these guys on a number line to find the intervals of increase or decrease. So that's what we do next. So
I think it's 0.54.
that would round to 0.54?
Yeah.
Okay. Mix that. Okay, so so I have critical numbers, right? Are there any other possible critical numbers? Does anybody recall how to find critical numbers? This is one way. There's another way critical numbers pop up.
When the derivative is undefined.
If the derivative is undefined, right. So I need to think about that. So is 3x squared minus 8x plus 1 ever undefined, or is it defined for all real numbers? Yeah, it's a polynomial. It's defined everywhere. So the only critical numbers I get are when it's equal to 0. But for other functions, we do have to say, hey, is this ever undefined? Is that part of the domain? So it kind of depends. All right, so number line time. Blue will work. So this is part C, intervals of increase and decrease. So I mark off my critical numbers. So about, the first one would be 0.13-ish, and the other one is what was it? 2.54? All right. And then I usually like to put a little dotted line there. And then I have to pick test values. So ultimately, I do want to know what the original function is at those numbers. But I'm going to wait to find that. In the meantime, I'm using what's called the first derivative test, and which talks about just increasing and decreasing functions. So a nice number to test over here would be 0. And in between, 1, yeah, 1 or 2, but 1's way nicer, right? And on the other side, 3, I guess, or 10, or something that's not too bad. So I guess I'll go with 3. And what I care about really is the sign of the first derivative, but often we just have to calculate its value. So I want to know what's going on with f prime of 0, with f prime of 1, and with f prime of 3. So reminder, f prime of x is 3x squared minus 8x plus 1. Okay. If we plug 0 in there, the first derivative is positive. That means the function is increasing. And so this is typically what my notes are going to look like. I evaluate the first derivative, I make a note of increasing or decreasing, and I draw myself a little arrow to see it. Right? All right, if we plug in 1 there, we get 3 minus 8 plus 1, which is a negative number. Yeah. And so that means I'm decreasing here. Now, cubics are pretty well behaved. If it goes up and then down, it's probably going to go up again, but you always should double check because there are some functions that do not change across a critical boundary. So we do need to double check 3. So that would be 27 minus 24 plus 1, which sounds positive 4. No, greater than 0. That means the function is increasing and it is rising up like that. So I need, ultimately, again, I need this number over here. What happens when I plug in the critical number to my function? But the whole increasing, decreasing thing tells me that I have a maximum there. Then we'll have to evaluate whether it's relative or absolute. But for now, we'll just say, hey, there is a max. The max is whatever this evaluates to. I haven't calculated that yet. This is a continuous function that decreases and then increases. So over there, I must have a min. And I'm making note of that. And then it's a matter of calculating those functions. So now we need at least a scientific calculator. Graphing calculator wouldn't hurt either. Let's see, what was the last part? Maxes and mins?
Yeah, relative and absolute.
Yeah, okay.
Max should be like negative 1.94.
Okay, so let's see. I'm going to bring up Desmos. And function f of x is x raised to the third minus 4x squared. It's x plus 2. Does that sound right? Oops, something went wrong there. Oh, my square ended up in the wrong spot. I think that's what I wrote down. And I still have an empty square there. Okay, so there's my function. And then numbers I found were these, let's see, fraction, or let's go minus first, minus the square root of 13 all over 3. So there's, oh, the y value is about 2. So that would be this one right here, 2.065-ish. Yep, there's that one, and 0.13-ish. And then the other one, f of fraction 4 plus the SQRT 13 over 3, negative 4-ish. So I have about positive 2 for a max, and looks like that is a local max, right? And then negative 5-ish roughly for the min. So let's see, let's go 2.06 and negative 4.88 to 2 decimal places. So the max is about 2.06-ish and the min negative 4.88-ish. Could we find the exact value of that max and min? Yeah, but plugging in those numbers that look like that, I think they're called quadratic surds, if I remember right. That's kind of a pain to plug that into a cubic and clean it up exactly. So that's good enough there. Stating the intervals for part C more formally, f of x is increasing on the interval from, it's supposed to be a curly bracket, let's try that again. Negative infinity, all the way up to that left number, which we could approximate or state exactly. I'm going to state it exactly just for fun. 4 minus the square root of 13 over 3. Union the other endpoint on the other direction, so plus the square root of 13 over 3, comma, infinity. Right? That's what my number line analysis told me. So just double check. From this side, and the function heads that way forever. So forever, all the way up to that critical number, we're increasing. And from the edge of that critical number on, we're also increasing. Now, here's a question, the way I wrote my answer. Are we increasing at the critical number? No. At the top, we're just kind of like in a brief moment of pause. It's neither increasing or decreasing. So technically, I shouldn't put square brackets there. We'll usually put parentheses there. Because we're increasing right up to that boundary point, and then right after that boundary point, we're decreasing, but at the top it has a horizontal tangent line, which is neither increasing nor decreasing. So that's typically the way we write it. All right, so then f of x is decreasing where? From the first critical number up to the second one. And we'll use parentheses for that too. So parentheses from the first critical number, 4 plus the square root of 13. Oops, sorry, I got that wrong. Minus first. And then up to the second one. And you'll be asked in some of the homework questions for intervals of increase and decrease. And for those, it's often okay to type in approximations for each of these numbers, as long as you use like at least 4 decimal places. Should work out okay. All right, write a sentence that explains the maximum that we found. Write a sentence related to the maximum. We did one of these the other day in class. Let's see what you remember about how to write it. Make your best guess. So here's one fill-in-the-blank sentence for that. So I would say f of x has a maximum of about, it was 2-ish, right? 2.06-ish. When x was about 0.13-ish. Okay. So the maximum is the y value, but the x value got us there. We had to find the x value first that led us to the max or the min. So you want to be careful about that when you're answering questions about maxes and mins. Yeah, questions on that? All right. So I just want to go back to talking about the second derivative test, which I started but ran out of time last class. So let me bring up my little toy here. Tangent changing slope. All right. Oh, and then somebody asked me how I make it do this. And again, I can show you after class if you want to see this. So the observation we made in class is that if I look at the tangent line in this region, over here it's about 11, over here it's about 5, and then it's going to get to 0. So as x moves from left to right, this tangent slope is decreasing. And then as I move past there, it continues to decrease, -1-ish, -2-ish, -3-ish, and so on. So in this region right here, as x moves left to right, the slope is decreasing, which means the derivative is decreasing. So if I know the derivative is decreasing, then I know the function must be concave down. That's the observation I did the other day here. Okay. Well, how do we tell if a function is increasing or decreasing? We take its derivative. So we already have, we're talking about the derivative here, so we have to take the derivative of the derivative. So the second derivative tells us about concavity, okay? So the second derivative, magic tools disappeared. Does a few things. One, it describes the rate of change of the first derivative. Which consequently, the first derivative is our slope function. So I can also say it describes the rate of change of the slopes of the original curve. And the observation about the changing slopes on the original curve tells us about concavity. So the second derivative identifies intervals of the function being concave up or concave down. So summary here is it's going to be concave up if f double prime, the second derivative, if it's greater than 0. Because if the change is greater than 0, that means the slope is increasing. And it's going to be concave down if f double prime is less than 0. That means I have a negative change going on with the slope function, so the slopes are decreasing. And the observations we made was a decreasing slope makes the curve look concave down, and increasing slope makes the curve look concave up. So I'm going to double check in the picture that concave up thing. I'm not going to prove this. There's a proof in the book if you want to check it out. It's like the proof I made the other day that shows increasing to decreasing on a regular function gives you a max. Same idea. So if I go over here, so notice the slope here is going from -4, -5, -6, -7. And then all of a sudden there's this magic point where all of a sudden it starts going, so there's -8. Oh, now it's up to -7. And then it's up to -6. And then it's up to -5, 4, 3, 2, 1, 0. So that's kind of interesting. Somewhere in here, there's a point, maybe it's at the origin for this function, where the function goes from let's see, what are we doing here? We are a decreasing slope. Then all of a sudden the slope starts to increase to 0 and then steeper and steeper and steeper. Okay. So would you agree the slope is increasing? -7, -5, 0-ish, 2, 4, 6, 10, 12, 20, right? The slope is increasing. And the function is what shape over here? It's not a parabola, but it's concave up. Yeah, so a parabola only relates if there was an x squared involved here as the highest power. But here the highest power is 3. So a parabola can be concave down or concave up. A cubic can have both features. And there's this very special point right in between the change in concavity. Did anyone read ahead and see what that special point is called?
Inflection.
It's called an inflection point. Okay, and inflection points are important for a variety of reasons, which I'll get to in just a minute. All right, so we've got 3 important features of the second derivative. Another important feature, let's call this feature number 4, is that a change in concavity happens at what's called an inflection point. And I'm going to explain why as a walker, hiker, biker, I love inflection points. That's bizarre. Why would you like inflection points? So let's suppose, I'm going along this flat road area, and then all of a sudden a hill comes and is getting steeper and steeper and steeper. But do hills get steeper forever?
No.
No. Eventually, it starts to reach the peak and then comes back down. So in part of this curve, from here to say about there, the slope is increasing. In the first part of the hill, it ain't too bad, but as I move along, it's like, oh man, this is getting harder to hike or bike or walk, whatever I'm doing, or run. But then there's this magic point, red, somewhere over here, so that the slopes become a little less steep, and less steep, and less steep, and less steep, until I reach that point at the top where I'm horizontal momentarily, and then I start to drop again. So in this area up here, the slopes are decreasing. And that magic point where it shifts from an increasing slope to a decreasing slope, that's that inflection point. Okay. So let's see. The second derivative, if it's positive, it's going to give me that concave up region, which I have right here. And if this, so just note right here, in this situation right here, f double prime would be greater than 0. And then there's that magic boundary right there. And on the other side here, the second derivative is going to be what? Concave down, second derivative, less than 0. What was that?
Less than 0.
Less than 0. It's going to be less than 0 on that side because it's concave down over there. If I go from positive to negative, what do I have to hit in between?
0, 0.
I have to hit 0. So if there is an inflection point, if that happens, then at the inflection point, the second derivative has got to be exactly 0. Because I changed from positive to negative. So I can identify that inflection point. So we're going to use that idea on the function we were just playing with, identify where it's concave up, where it's concave down, and then we can identify the point at which it changes concavity. And then we'll use the second derivative for one more thing. So backing up a page just to see my original function, where to go function. Nope, one more. There we go. Okay, so that function right there. So I'm going to add a part E here. So part E is to find the second derivative, A, B, C, D, E, F, is going to find the intervals of concavity, intervals of concavity, B, B, C, D, E, F, G is going to be identify the inflection point. Okay, so find the second derivative. That's not too bad here. 6x minus 8. Excellent. So to find the intervals of concavity, that's just like the intervals of increase and decrease. We first find potential inflection points by setting this equal to 0. And then we see if there's a sign change on either side. So we're going to do a whole number line thing again. I'm going to add a new page here. So for concavity, we first set f double prime of x equal to 0. Well, let's see. We do that, we're going to get, what was it, 6x minus 8 equals 0.
Mm-hmm.
So then x is equal to 8/6, or what do we call that, 4/3, which should be 1 1/3.
Can't really believe it is 4/3.
Yeah, mixed numbers are dangerous when you're calculating, but on a number line, it's nice to know it as a mixed number, because then you can say, oh, to the left of that, a very nice number would be 0, yeah, whenever I can use 0, that's like my favorite number to plug in. So I'm gonna go for 0. And on the other side, I could go for 2. And so then what I do is I just say, well, if I plug 0 into f double prime, I want to know what the sign is. So if I plug in 0 here, I get -8. -8 on a good day is less than 0. So negative second derivative tells me the function is concave up or concave down.
Is concave down.
Down, correct. Yeah, so this tells me that I am concave down here. And I'll give you a hint on how to remember that in just a sec. On the other side, don't just assume it's concave up. Double check, plug in the number. F double prime of 2, 12 minus 8 on a good day is 4. 4 is definitely a positive number, so I must be concave up on the other side. Concave up on that side. And like I do the arrows for increasing and decreasing, I usually like to draw in the concavity too. Just helps my visual brain put it all together. We haven't quite, do we have an inflection point first? The answer is yes, because there was a change in concavity. We went from concave down to concave up. So we definitely have an inflection point. We haven't found it yet. To find it, you have to plug in that number to the original function. So I would then have to say, well, what is f of 4/3, by the way? So off to GeoGebra. Oh, I accidentally deleted that graph. Bummer. Do it again. So f of x equals x cubed minus 4x squared plus x plus 2, if I have it right. And I want to know what f of 4/3 is. And, oops, wrong place. Desmo says it's about negative 1.4-ish, approximately. And so I'm going to actually plot that point by just turning this into a point. So I want 4/3 for x, comma, oops, comma, f of 4/3 for y. So that's this point right here, which is about 1.333, negative 1.407. And that's the point where I shift concavity. Does that look reasonable on this picture as a point? Yeah, so if your point ends up like way up here, oops, something's wrong, or over here, something's wrong. It should look like a possible place where you shift that concavity. Okay, so that is our inflection point right there. All right, I'm going to show you one more use for the second derivative. And to do that, I want you to go back to the sketch you made of the number line here. And I'm going to erase the identifying extreme notification there. And what I'm going to do instead is I'm curious as to what the second derivative says about the critical number. So I'm going to plug the critical number directly into the second derivative. Okay. I'm going to do that here too. Second derivative, I'm going to plug in 2.54-ish. So remember, my second derivative, so the first derivative is up there. Second derivative was 6x minus 8. Mm-hmm. So really, the second derivative, I don't usually care about its exact number, but I care whether it's positive, negative, or 0, because that tells me concavity. Okay? So instead of using 0 as the test number like we did before, couldn't I use 0.13 as the test number? Because it's to the left of that possible inflection value. Yeah. And 2.54-ish, is that to the right of that 1 1/3? Yeah, so I could have picked those numbers to test, and they would tell me the concavity also. So if I plug in 0.13, that's about 1/10 of 6, which is about 0.6. 0.6-ish minus 8 is definitely a negative number, agreed? Mm-hmm. Okay. So this is less than 0. That's really all I care about, which tells me if the second derivative is negative, what's my orientation here, up or down?
Down.
It is concave down. If I'm concave down, what type of extreme value must this be?
A maximum.
It must be a maximum. Yeah, so the second derivative can be used to determine if something is a relative max or relative min in a given region. The first derivative tells us that too, right? But the first derivative, so there's a trade-off. With the first derivative, I have to check a number on the left side and the right side to make sure it's going up and down or down and up. Second derivative, I just plug one number in, the critical point. Downside, I have to find the second derivative. Sometimes that's easy, like here, but sometimes that's hard, right? So here, it would be easy to find the second derivative and plug in the critical number. Whereas if this was some like rational function, second derivative might be quite a hassle. Okay. So there are trade-offs, but they both tell us useful information. If I plug 2.54-ish in here, let's see, 2.5 times 6 is going to be like 15-ish. Minus 8 is definitely a positive number. Positive value of the second derivative tells me that I am concave up in that region. So then I must have a relative min in that region. So the second derivative not only tells us concavity, but that concavity at critical points tells us if we have maxes or mins. Are you okay there?
Mm-hmm.
It's a lot of information. Section, what is the section 5 we're on right now?
Mhm.
There's a lot of stuff in section 5. Yeah, so we're probably going to have one more day on it. The schedule said we had 2 days up to today, but we'll probably need more time. All right, let's look at another example. I'm going to go back to when I started on Friday and didn't finish because we ran out of time. It was a rational function. There it is. So at the end of the notes, you probably have this in your notes from Friday. So from last Friday, I gave a function, I don't remember what I called it, but I'm going to call it f of x today. And it was x squared minus 4x plus 5 over x minus 2. And let's see, do I have the derivative of that here in my notes? Thought, I didn't write it down. Oh, I must have wrote it somewhere else. Anybody happen to have its derivative in your notes? I don't have to do it all again. Come on, we did this together.
And when did we do it?
Friday? I don't remember what the date was on Friday.
What were we going over?
Oh, it's derivative?
On Friday, we were going over increasing and decreasing. We can do it again, it'll be good practice.
I think it would take us less time to do it again than it's gonna take them.
Find it in the notes. Okay, so I'm gonna do it actually a slightly different way, and if you find it in your notes later.
I have it.
I wrote it.
Yours, I don't know, you have it? Okay, there you go.
I got x squared minus 4x plus 3 over x minus 2 squared.
I'll say that again, x squared,
Minus 4x
yeah,
plus 3
plus 3.
over x minus 2 squared.
Okay. So I'm gonna look at this a slightly different way just for fun. I mentioned that we could do either long or synthetic division on that. Okay, so I'm gonna go to a new page and do that. I'm gonna do synthetic division. So with synthetic division, 2 is what makes the denominator 0, so that's what's used in the synthetic division. And then I need the coefficients at the top, which are 1, -4, and 5.
Are we doing this to the derivative or the original function?
The original function. Yeah, this is the original function. Because I'm just going to show you that sometimes this can make a rational function easier to deal with. So synthetic division, bring down the 1, multiply by 2, add coming down, multiply by 2, add coming down. This number right here is your remainder. So what this tells me is that x minus 2 goes into the numerator, x minus 2 times, plus a remainder of 1 out of the original denominator, which is x minus 2. So this is another version of f of x. Okay. Now I could also write this, instead of this as a rational part there, I could say this is x minus 2 plus parentheses x minus 2 to the power -1. True?
Mhm.
So then the derivative here does not require us to use the quotient rule. So the derivative here would be the derivative of x is 1, the derivative of minus 2 is 0, plus the derivative of this thing right there would be a -1 times x minus 2 to what power?
To the zero.
You
No,
reduce by
negative
1, so it'd be -2. Yeah. And then we also, the chain rule says I have to multiply by the derivative of the inside of this thing. What's the derivative of x minus 2?
1.
It's just a 1. I'm just going to write that in just to be thorough. So cleaning that up, I get 1 minus 1 over x minus 2 squared if I put it back in rational form. So although the derivative was easier, I had to use synthetic division to get there. Trade-offs. But we know a lot of algebra. All right, so I'll come back to that later, but that's just another way to look at it. So if I did combine the 1 with the minus 1 over that, it should clean up to be this thing over here if I wanted it to be. All right, so things to consider here. In the original function, as far as the domain goes, just to review some things we talked about last time, x cannot be 2. In the derivative, x still cannot be 2. So when I'm thinking about critical numbers, although the derivative is undefined at 2, so is the original function, which means 2 cannot be a critical number. It would only be a critical number if it was undefined here but defined there. With me? So then I just need to consider critical numbers here are only when the numerator equals 0. Because the only time a fraction can equal 0 is if the top is 0. So f prime of x equals 0 if the numerator, x squared minus 4x plus 3, equals 0. And did that sucker factor? I think it did. Factored as x minus 3 times x minus 1.
Mm-hmm. Correct.
So that means the critical numbers here are x equals 3 or 1. And so then we whip out our number line. Almost out of time. We can finish this one next class apparently again. So things to note here, 1 is an important number. What was the other one? 3 is an important number. And 2 is an important number, but one I just have to stay away from. So I'm just going to make a note. 2, I just can't touch it. So as far as test values go, I need to test values that are on one side of 1. So for example, 0 would be an okay test value. In between 1 and 3, I can't pick 2 as a test value. Remember I accidentally did that last Friday? I would have to pick something like maybe 1.5. And then on the other side of 3, perhaps I would pick 4 as a test value. And I would want to know what is f prime of 0, positive or negative? What is f prime of 1.5? Is it positive or negative? What is f prime of 4? Is it positive or negative?
Would we want to have a value between 2 and 3?
So 2 is not a critical number. So it's the function can't change from increasing to decreasing if there's not a critical number there. The critical number is either going to come from a point that the derivative is undefined, but the function is defined and 2 doesn't fit that bill. Yeah. So when in doubt, test the other number just to be safe, but technically we shouldn't have to here. Okay. So a couple other things we're going to do with this. We're out of time for real. We're using derivatives to analyze functions. So calculus, part of it is derivatives. Another part of calculus is limits. We're going to come back to limits tomorrow. And we're going to look at limits at infinity. Limits at infinity come in a couple of different ways. If a number makes the denominator 0, that often involves infinity. We've seen that before. And then we can also let x go to infinity or negative infinity and see what happens, which means we might come into contact with asymptotes. So the next section is about end behavior and asymptotes. We do need to spend a little more time on this section. So tomorrow we'll continue with section 4.5 and we'll probably start section 4.6 tomorrow. All right, have fun, do good math. Yeah, this section is meaty. A lot of stuff in it.
What do you want our test corrections?